Welcome to the Chapter 7 Screencast, the first part dealing with covalent bonds and molecular structure. As you've seen, all matter is made up of about 100 different elements, and these basic elements, these substances, can combine to form chemical compounds, and each chemical compound has a definite composition that can be represented by a chemical formula. Some examples of these are H2O, water, NaCl, sodium chloride, NH3, ammonia, C12H22O11 or sucrose, PbI2, lead 2 iodide, calcium phosphate, Ca3PO42, and plenty more where those came from. Now, we've already seen a type of compound that typically forms when we have a metal react with a nonmetal. So we're dealing with substances on this part of the periodic table, the metals, reacting with something on this side of the periodic table, the nonmetals, and in general, metal atoms lose electrons and form cations or positive ions, and nonmetals gain electrons and form negative ions or anions. And of course, a classic example is sodium chloride, where sodium atoms make sodium ions, chlorine atoms make chloride ions, and then the positive and negative ions attract each other. So these ions attract, and they make an ionic compound. And what we know about ionic compounds is that the attraction is an ionic bond, and ionic compounds are overall neutral. So the positive charges and the negative charges balance each other out. Examples of ionic compounds are sodium chloride, magnesium oxide, aluminum oxide, ammonium acetate, and plenty more of those as well. Now, we've already dealt with ionic compounds with gain and loss of electrons, but it turns out there's another type of chemical compound that generally forms when a nonmetal reacts with another nonmetal. So we're dealing with elements in the upper right corner of the periodic table. And when nonmetals react with nonmetals, the atoms don't gain or lose electrons, they share electrons, but they also are achieving typically a noble gas electron configuration like ionic compounds do. And an example of this would be chlorine. So a chlorine atom has 7 valence electrons, or 7 dots around it in the Lewis symbol. Another chlorine atom also has 7 valence electrons, or 7 dots, and each of these atoms is 1 electron short of an octet or a noble gas arrangement. And if one atom were to lose an electron to the other, then one of the atoms would have an octet, but the other would be even worse off than it was before. So the solution to this is that both atoms share electrons. So the total of 7 electrons from this chlorine and 7 electrons from that chlorine give us a total of 14 electrons in a chlorine molecule, but the 2 electrons here in the middle are shared between the 2 chlorine atoms, and this chlorine has 8 electrons around it, so it has an octet, and this chlorine has 8 electrons around it, so it also has an octet. And the 2 electrons in the middle do double duty, they count for both atoms, and that shared pair of electrons is what's known as a covalent bond. Now, each shared pair of electrons, as we just said, is known as a covalent bond, and what this bond does is it kind of glues the atoms together. So here's an atom with its nucleus, positively charged, bonded to another atom or near another atom with a nucleus, positive charge, and the nuclei, both being positively charged, repel each other. But there's electrons here, and the electrons are negatively charged, and these negatively charged electrons attract the positive nucleus here, and they attract the positive nucleus there, and that glues, in a sense, these 2 atoms together. There is an optimum distance between the nuclei of the 2 atoms, and this is called the bond length. And the bond length corresponds to the arrangement of the atoms that has the minimum energy so it's the most stable arrangement for those atoms. And as an example of this, if we're dealing with hydrogen, so two hydrogen atoms combine to make a hydrogen molecule, and if we do a graph of distance between the atoms and that graph is versus energy, then the zero of energy could be considered when the two hydrogen atoms are really, really far apart. So they're so far apart they don't interact with each other, and the attractions are essentially non-existent. There's no bonding. But if these two hydrogen atoms are moved closer and closer together, so the distance between the two nuclei gets less and less and less, eventually the electrons in one atom are attracted by the nucleus in the other, and vice versa, and the energy goes down somewhat. And the energy keeps going down until it eventually reaches a minimum, and this minimum is the bond length. In this case, for hydrogen, it's 74 picometers. And then if you were to try to push the atoms even closer together, then what happens is the nucleus in this atom and the nucleus in the nearby atom, those are getting too close together, and the positive nuclei repel each other, and the energy goes back up. So too close, too much energy; too far away, more energy. Just right bond length distance is the minimum energy, and again for hydrogen the minimum energy is at the bond length of 74 picometers. For different atoms bonded together, it'll be a different value. So each specific bond in a molecule has a specific bond length and a specific bond energy. These energies are given in tables, and they are typically in kilojoules per mole. So hydrogen, H2, hydrogen-hydrogen bond, the bond energy is 436 kilojoules per mole. That's how much energy it takes to break apart a mole of hydrogen bonds. If we're dealing with a different atom bonded to atom, so for example carbon bonded to carbon, single bond, that's 350 kilojoules per mole. And if you look at the table, you'll see that in general bond energies are in the several hundred kilojoules per mole range. Some are quite high, like the nitrogen-nitrogen triple bond is 945 kilojoules per mole, and some are fairly small, like for example iodine to iodine is only 151 kilojoules per mole. As we saw before, bond lengths are determined, and they give us values or approximate values for atomic radii. So if we know that a hydrogen atom has a radius of about 37 picometers, then roughly doubling that would be about the bond length between two hydrogen atoms. And if we were to take the radius of carbon, let's say, along with oxygen, then the sum of those two radii would give the approximate bond length of a carbon-oxygen single bond. So these are approximate values, can help us determine bond lengths from atomic radii. Some examples: the hydrocarbons C2H6, C3H8, and C4H10, plus many more, all have single carbon-hydrogen bonds, and the bond lengths are relatively similar, but C2H4 has a carbon-carbon double bond, which is much shorter and much stronger, and C2H2 has a carbon-carbon triple bond, which is even stronger and even shorter, and we'll deal with multiple bonds in a bit. Now, a thing to remember is that chemistry is all about what the valence electrons are doing. So it's the dance, the song of the valence electrons, and we're going to keep focusing on valence electrons throughout. And also remember that Lewis had this great idea, which is a really useful way to describe atoms and ions and molecules, as well as ionic and covalent bond formation, and ionic and molecular compounds in general. And his idea is to use electron dot symbols, where the symbol of the element represents the nucleus and the inner shell electrons, and dots represent the valence electrons. So let's do one repeat of something we've seen before. which is Lewis symbols used to represent ions and ionic compound formation. So let's do the example of magnesium reacting with oxygen. Magnesium has 2 valence electrons represented by 2 dots. Oxygen has 6 valence electrons represented by 6 dots. And what can happen in the formation of a magnesium oxide compound is that one of the valence electrons from magnesium can fill the missing electrons spot, in a sense, in the oxide, or oxygen, which is going to become an oxide, and the other one can fill the other missing spot. And what ends up happening then is we have a magnesium. Now it's an ion because it no longer has its 2 valence electrons. And we have an oxide, which is also now an ion because it has 2 more valence electrons. And we have the magnesium oxide substance where the positive magnesium ion attracts the negative oxide ion. And that's how we could represent magnesium